Yeah, that is the heat. C is the heat for 1 mole for 1 day.
Mm.
Got it?
Yeah.
At constant volume. Okay. So whatever the heat which we give, that will be the moles which we took into CV, into the temperature change which we observe. Got it? Clear?
Yeah. Yes.
That's what we discussed. That's all. And if we are doing at constant pressure, this week I told you just now. Constant pressure doesn't means the expansion can take place. So whatever the heat I'm giving, part of it is being retained inside the gas, and part of it is used to do the expansion work. Heat given at constant pressure is known by the name of enthalpy change, or the heat change at constant pressure. It can be measured by the change in temperature difference multiplied by molar heat capacity at constant pressure. Okay, they will give you the value, so don't worry about it. Got it? Into number of moles. There is a relationship between the delta U and delta H. This you should remember. H equal to U plus PV, delta H equal to delta U plus delta PV you can write, because the pressure is constant, so P delta V. P delta V is change in number of moles of gases into RT for reactions. Okay. You need to calculate the final moles of gases minus initial moles of the reactant. Here, what is the relationship between the Cp and Cv of a gas? Molar heat capacity at constant pressure, molar heat capacity at constant volume. Okay. This is basically Cp minus Cv equal to R. R is a gas constant whose value is if you are calculating the work, take R as 8.314 joule per Kelvin per mole. Take R as or take R as 0.082. Yeah, good evening, Aisha. There is one more relationship. Okay, that is these things you should remember because they will be useful in your physics also. Cp by Cv, the ratio of molar heat capacity, means whatever the heat which is required by 1 mole of gas for 1 degree rise. Okay, that is equal to gamma. Got it? Cp minus Cv equal to R. Cp and Cv are the heat for 1 mole and 1 degree. Is it clear or not?
Yes, sir.
This is a constant. Sometimes they give you the value of gamma. Okay, otherwise you can find it out.
So what's the smaller?
Pardon? No,
What's
this is
the
not.
smaller?
This is not small r. This is like this. Something like that. Okay. Looks like small r. This is known as gamma. Greek letter. Is it clear?
Yeah.
Yes, sir.
Okay. This is Poisson's ratio. Just remember it. Okay. And this is known as Maer's equation. So they will give you the values of either one of them. Okay. Remember these two things. They are very, very common for chemistry, but in physics it will be more common. Okay, because you have this in the physics also. What are the values of Cp and Cv? Either you it will be given to you like it is given in some question I gave you, right? Or if it is not given, I will tell you a trick how to find Cp and Cv. Monatomic gas means
A gas which have only one atom.
yeah. Example. Noble gases.
Helium.
Yes. Nabila, what could be the other noble gas?
Mm,
Neon. Aisha, what
okay.
could be the any other noble gas? Aisha. Argon, krypton, xenon, noble gases. They don't combine with any other atom. Their octet is complete. You must have studied in your 10th. You know it very well. So they don't. They have just single atom. Okay. Okay. Cv is 3 by 2 R. This is 5 by 2 R. Just add one R to it to get, because Cp minus Cv equal to R, Cp equal to Cv plus R. Got it? Cp is higher. Diatomic gas examples: N2,
H2O2.
H2,
Mm,
O2, which is 5 by 2 R. And to get the Cp, Cp equal to Cv plus R, so 7 by 2 R. Got it? For triatomic, it is 9 by 2 R and 11 by 2. Got it? Gamma is 5 by 3, that is equal to 1.67.
So how are you calculating it, or is it like fixed values?
So it is calculated by degrees of freedom. For example, it will be covered in, actually it is calculated by degrees of freedom, right? And degrees of freedom means on how many different types the molecule can rotate or move. Okay, that is degrees of freedom. That will be covered in kinetic theory of gases in physics also, same thing. So as of now we can keep it on hold, right? And but it is very easy. Once you have the KTG covered, then we can discuss very easily, because this kinetic theory of gases, it was there in class 11, but now it has been removed from the syllabus because it is there in the physics also. So same chapter was studied twice. Okay, so don't worry about it, right? As of now, you can remember it. 1.4 gamma value, and this is 11 by 1.2. Got it. So these are the types. Triatomic gas. Can you give me the example of triatomic gas? O3.
SO3.
That is tetratomic. SO2. Got it. Or they will give you the values also, and with the values you can find the CP and CP. They can give it to you in the question also. They can give it. Yes. So next, how is delta U calculated?
By
How is
adding heat and work
energy
done.
change calculated? Pardon?
By
By
adding heat and work done.
adding heat and carrying out a reaction in closed container. That is known as bomb calorimeter. Okay. Delta U is calculated with bomb calorimeter. Okay. So let me move on to the next part of delta H value. What is delta H?
Change in enthalpy.
Enthalpy change, or in simple language, what should I say? Heat change. The sign convention is just the same. The sign convention is same as that of it is sign convention is exactly same as that of the sign convention of Q. Okay, if the heat is giving into the system, that is positive. So what is the sign convention? If the heat goes into the system, it's taken as positive. And if the heat is given out of the system, heat released is negative. Got it? So can you give me the sign of delta X? Hmm.
It's negative for combustion.
Yeah, negative. Because it releases heat. If you want
Positive.
to melt ice, you need to put in heat. Okay. Then only ice will melt.
Negative.
Boiling of water, you need to heat. Boiling of water, heat is given out or heat is being sent into water.
So
And
heat is being sent.
To water, right? So for the system we are talking, water is taking the heat from it. Got it?
yes,
You have studied decomposition reaction, Aisha, in class 10. A compound is broken
Copper is broken down into several components.
several compounds or elements. And breaking something, will it release it or you need to provide energy to it? You want to put in heat
Wait,
or heat will, yeah,
decomposition reactions are always endothermic in nature.
always endothermic because you are breaking something. To break something, it's not that it will break automatically and it will give heat. No, you need to put in heat, that then it will break. So, is it clear?
Yeah.
yes,
And there are this is basically delta H for a physical change or a chemical change. Very simple. And what you do over here is you first notice a sign. That sign actually tells you. And there is one more thing by which it can be written. It can be written like this: melting of ice. If I say so, you are having H2O solid. Okay. You are giving heat. can write it like this. Heat is being provided to the ice. This is basically ice. Got it?
Yes, sir.
And or I should write it like this. Don't write a heat as reactant or product. This is one and the same thing. Okay. Normally we follow this kind of terminology. Okay. And because you are doing it at constant pressure, you are giving heat. It is like this. Is it clear or not?
Yes, sir.
Whatever the heat given, that depends upon the mass, amount of water, amount of ice which you are melting. So I'm going to use one more term. Intensive property and extensive property. Intensive property are those properties which do not depend upon the amount of substance. Can you give me some example of intensive properties like boiling point, melting point?
So what is P? Oh, point.
Boiling point or melting point?
Okay.
Boiling point, is it different for 1 gram of water and is it different for 1 kg of water, or is it the same? At what temperature
It's
water?
the
Yeah, it's same. 100 degrees Celsius. Melting point is also same. If I say molar heat capacity, that is for 1 mole. That will be same for any amount, because for any amount which you put, you are not bothered with the amount, you are actually calculating it for 1 mole. Molar heat capacity. Extensive properties. They depend upon the amount of substance taken. Example, internal energy, enthalpy. If I took small amount of gas, 1 mole of gas, in total internal energy is going to be less. If I take 100 grams or 100 moles, that will have different internal energy. Heat of reaction, that depends upon the amount of substance. Is it clear?
Yeah.
Heat capacity. There are two different things. Molar heat capacity, I will write it like this: molar heat capacity. Or heat capacity. Molar heat capacity is for 1 mole only. Whether you took 100 gram or 5 gram or 200 gram or 1 kg, you calculate it for 1 mole. For 1 mole, it is going to be remain constant for a given substance. Heat capacity is the total amount of heat which need to be given to a body to raise the temperature by 1 degree. So that will depend upon the mass of the body. Suppose if there is a small ant and if you are giving heat to that body to increase a temperature by 1 degree, that is going to be less. And if you are taking an elephant, the heat given, total heat, that is the heat capacity for 1 degree rise in temperature, whatever the heat is given. Is it clear?
Yeah.
It is the total heat. So extensive property depend upon the mass. Pressure and temperature are intensive properties. Mole is an extensive property. How many moles are taken, that depend upon the mass, given mass by mole. Got it? So I would like to
So
say, pardon?
can you repeat?
Yeah, moles n. A mole is an extensive property. How many moles you took, that depend upon the mass which you are taking. Is it clear? Suppose if you have taken 18 grams of water, 18 gram in 1 mole of water, right?
Yeah.
Yes, sir.
If you have taken 9 grams of water, that is half mole. Aisha, am I audible?
Yes.
Sorry, getting my point. So extensive property depend upon the mass or the amount. Mole depend upon the amount. If I have taken 9 gram of water, mole will be mass by molar mass, 9 by 10, half mole. Got it? So I would like to say that the internal energy and enthalpy, total enthalpy, are extensive property. They are going to depend upon the amount of substance taken. Got it?
Yes, sir.
Yeah.
Or delta H is normally used for measuring the heat of reactions. Okay. So now we are going into the applications of delta H values. Right, they are very simple. Okay. Very easy to calculate. Right. So enthalpy change for a reaction. Enthalpy change for a reaction. Just now we have discussed this. So whatever the heat change which is there, which is taking place for a reaction is known as enthalpy change for a reaction. Okay. It is basically the heat change. For a chemical reaction. That is called enthalpy change for a reaction. Got it?
Yeah.
Yes, sir.
Okay. So different reactions will have different values. So, but the same reaction can also have different uh, values. Okay. So, when you take different temperature and pressure, you can have different values of delta H for a same reaction. Okay. So, what you do over here is you calculate standard. This is represented by delta H. Delta H reaction. So we have seen about various types of reactions or changes, and we have seen just the sign of delta H values. Okay. Now we are basically looking at the standard, because these values will have delta H will have different values at different temperature. Got it? At different temperature, the same reaction at different pressure also, you will have different values. Got it? Because the
Yes, sir.
delta H value, I should write here, then I should introduce this, depends upon of reactants and products. It depends upon it also depends upon the amount or the moles of the reactant and product which you have taken. Is it clear? So the delta H of a reaction depends upon many factors. Got it? It depends upon
Yes.
the temperature, pressure, it depends upon the physical state of the reactants and products which you have taken. Okay, it depends upon the uh, state or the allotropic condition which you have taken. Is it clear? It depends upon the amount of substance. Surely the heat liberated by burning 1 gram of methane and 1 kg of methane will not be same. Amount or moles. Okay. So what you do over here is you, because it depends upon so many factors, so you fix some of the factors and you call it standard enthalpy of the reaction. Standard enthalpy change for a reaction. Okay. So standard enthalpy change it is also represented by delta H. Okay. But you put a subscript. Delta means change. H is the heat change at constant pressure, enthalpy change. And this is the sign used for standard enthalpy change. For a reaction. Because enthalpy change can have different values at different temperature, different pressure. So what you do is, so suppose all of us do a same experiment. For example, Nabila, Aisha, Ma, all you do, and myself, all four of us do a same experiment. But all four of us have taken different temperatures. I'm doing at 100, Ma is doing at 25 degrees Celsius, Nabila is doing at 50 degrees Celsius, and Aisha is doing at 100 degrees Celsius. So the delta H value will be different. So how to compare the values? It could be a problem for a same reaction. So it is better because in whole world we cannot have pressures and temperatures same. So how we will compare the heat of a reaction? So what we do for carrying out a chemical reaction or for measurement purpose, we have fixed the conditions, okay, for the measurement of enthalpy change, and that is known as standard enthalpy change for a reaction. It is represented by delta H with a subscript. Okay, I'm showing you the subscript. Okay, and I'm writing the definition. So it is the enthalpy change for a reaction. When when all the participating reactants or products are in their standard states. So in their pure form at 1 bar, 1 bar pressure, got it? Temperature you can accordingly decide whatever the condition you are taking. So at that temperature, okay, what is the state of that natural state of that substance? That will be the standard state. Are you getting my point?
Yeah.
For example, if you take water, okay, at 25 degrees Celsius, and 1 bar pressure. So what is the standard state of water at this temperature?
Pure form का water.
Yeah, is it solid?
Liquid.
Is it
Room
liquid?
temperature.
Yeah, it is liquid. Got it. Is it clear?
Mm.
So normally you take 1 bar pressure and 298, 1 bar pressure and 298 Kelvin for the measurement of standard state of the substance. So standard state of water is liquid. So if you are measuring the standard enthalpy change, okay, it is should be at 25 degrees Celsius and 1 bar. Got the point or not? Right?
Yeah.
So standard enthalpy change, and the reactant and product should be in their standard states, right? So standard state, for some of the uh, reactants, and for some of the reactant we are going to introduce as we move ahead. Okay, so that is known as standard enthalpy change for a reaction. So standard enthalpy change is the enthalpy change for a given reaction. Okay, it is the enthalpy change for a given reaction at 1 bar pressure and 298 K. So that is basically gives you and that is the value which you use for the comparison. Okay. For example, H2O liquid to H2O gas. So this is the vaporization happening. Okay. So these standard enthalpy changes are further given name Standard enthalpy change is the name for all of them, okay, for all reactions. For each specific reaction, whatever is happening accordingly, that standard enthalpy change is given, allotted its name. Is it clear? So standard enthalpy change for, let's say, vaporization, standard enthalpy change for fusion, standard enthalpy change for vaporization is written like this. You write a subscript at the bottom of delta, and accordingly you write the value with sign. That is, let's say, plus 40.79 kilojoules per mole. Are you getting a point or not? So this is known as standard enthalpy of vaporization of water. So it is the enthalpy change for a given reaction, standard enthalpy change for a given reaction. And I'm not using the now common term given reaction, I'm using the specific term as per what is happening. You can see what is happening. The liquid water is changing to gas. So it is the vaporization. Okay. So whatever the amount of heat required to vaporize, so how will you define? Suppose if somebody asks you, define enthalpy of vaporization or a standard enthalpy of vaporization, what definition will you write? Tell me.
It is the change in heat.
The the boiling point to when it starts to evaporate.
Yeah. It is the amount of heat required to vaporize 1 mole of liquid at a constant temperature and pressure of 1 bar and 298 Kelvin. Okay, got it? Is it clear? So you write it like this. This is known as thermochemical equation, where you write the equation, and along with the equation you write the symbol of delta H also with the sign for 1 mole of reactions. Make sure that this equation is balanced. Is it clear?
Yeah.
Very important. This equation is balanced, and whatever the coefficients are there, so that delta H is given for those number of coefficients only. For example, if I do it for 2H2O, to giving 2H2O gas, the heat will be 40.79 into 2. Are you getting my point or not? It is not 40. It is for 1H2O to 1H2O gas. It will be twice. So this representation is known as thermochemical equation, and this is like the mathematical equations, as you can see, right? And this mathematical equation is basically used to add or subtract, okay, to get the value of a new equation. Okay, that we will do in a while. So what is enthalpy of fusion? Let's take one more example. Standard enthalpy of fusion. What do you mean by that?
It
What do you
requires to
mean?
combine two compounds.
What do you mean by fusion?
Fusing together,
Combination.
the
It is
mixing.
melting. Yeah, fusion means that also when two things are fused together. Yeah. In chemistry, it means basically standard enthalpy of fusion. Fusion means melting. So for a standard enthalpy of fusion, H2O solid. Fusion means melting. Got it?
Yes.
To H2O liquid. So whatever the heat required under standard condition of 1 bar, I will write the subscript, not completely, but just small initials that represent delta fusion H standard condition equal to plus because 6 kilojoule per mole. Okay, is it clear?
So the subscript is only a 0.
This is the subscript is this fusion. This is the
Mm.
superscript.
Oh, sorry.
Superscript is actually this not with a bar.
Mm. Okay.
Delta is not. Okay. So
Okay.
some places you use this also, just a not. Delta is not. And some places you use delta is not bar. Okay. Is it clear? So
Yes.
standard enthalpy of fusion is the enthalpy change accompanying the melting of 1 mole of a solid substance. This is for water. Not only for water, you can define it for other elements also, other compounds also. So for 1 mole of the solid compound or substance in its standard state, okay. So whatever the heat is required to melt 1 mole of a substance in a standard state, that is called enthalpy of fusion. Is it clear or no?
Yeah.
Yes, sir.
So suppose if I give you find the, I have given you these two values. I have given you these two thermochemical equations. Got it? I give you one question. Hmm. So I hope all of you can see this.
Yeah.
9 grams of water in the solid state under standard condition. That also you can write in the bracket. So change it completely to 9 grams of vapor. So solid to liquid and liquid to vapor. I should write these two equations. You start from the solid, change it to liquid first. Then from liquid, you change it to gas, vapor. This much heat, the standard enthalpy change is basically, this is fission plus 6 kilojoules per mole. Very, very important to note that. This is delta vaporization under standard condition. Let's say, let's keep it 41. Okay, let's round it off to 41. Is it clear or not? These data
Yes.
will be given. Okay. So I am asking what is the amount of heat required to change the 9 gram of water from solid state to 9 gram of
47 kg by mole.
under standard conditions. Okay. So what should I do is, I want from here to here. Got it? These are thermochemical equations. They are treated like mathematical equations. Okay. Mathematical equations can be added. They can be subtracted. You must have done in your class 10. They need to be multiplied with certain coefficient. Okay. Then they can be added. Okay. Not subtracted. Is it clear? So I can add these two equations. If I add these two equations, this is on the right hand side, this is on the left hand side, this will get cancelled. Equation 1 plus equation 2. This is actually what makes us very convenient. Okay, these mathematical equations can be added, subtracted. Okay, just these thermochemical equations just behave like mathematical equations. Okay, but whatever you are doing with these two equations, you should do the same thing for these two. The delta H is going to be equal to 6 plus 41 because I have added these two equations. So it is going to be 47 kilojoules per mole. Okay, per mole of this equation, that is for, in this equation has 1 mole of water. Okay, so that is for 18 grams. One is not mentioned over here. It is quite obvious. It represents 1 mole equal to 18 grams. Of water. You require how much heat? 47 kilojoules for 1 mole. Okay, of equations.
So why
1
do
mole.
we need to subtract the H2 in liquid form?
If you add these two equations, H2O solid plus H2O liquid will be there on the left hand side. H2O liquid and gas will be there on the right hand side. It will be this kind of equation. A plus B is B plus C. Got it? So if the same thing is there on both the sides, it is unchanged. Okay, so let's remove it. It's not changing, it's not, it will get cancelled. Got it? Are you getting what?
Yeah.
So A get converted. So but you added the two equations to get this new equation. So you add accordingly, you should add the delta H values also to get the delta H standard enthalpy change for the final equation. And this equation has 1 mole of water. So, but the question is asking about the half mole of water. You need to find out, because this equation is in terms of moles. It is not in terms of mass. So this 9 gram is half mole. 9 by 18, half mole. Given mass by molar mass. Got it? So basically this is half mole. So for half mole, for 9 grams of water, I will need half of it. Got it? So this much heat I need. Is it clear or not?
Yeah.
Got it? So
Yes.
very these equations make our life very easy. Okay, in terms of calculation, doing calculation with respect to equations, chemical equations. Okay, and we can also add these equations, subtract these equations. Okay. You can add and subtract, and accordingly you should add and subtract the delta H values, right? And you can get the delta H value of a new reaction which is not initially given. Got it? So now let's move on to enthalpy of formation or standard enthalpy of formation. I should write standard everywhere. Standard enthalpy of formation. Okay. Delta H, delta HF naught. So it looks something, what can we expect from the name? What could be the definition? If we talk about the standard enthalpy of formation, what it may
The heat
be of
required
a
when a
compound.
compound is being formed.
Yeah, 1 mole of compound is being formed under standard conditions. Okay. Something like that. That is being indicated by the name itself, enthalpy of formation. Right? But we need to have certain amount of precautions. Okay. Something extra we need, some details are there which we need to take care of. Is it clear? So, but overall, what you said, Maha, is correct, right? So, in standard enthalpy of formation, it is the enthalpy change for the formation that you told very clearly. But we can make 1 gram, we can make 1 mole, 2 mole, 3 mole, 10 moles, okay? Because it is standard enthalpy change. So let's homogenize it to 1 mole. So it is the standard enthalpy change for the formation of 1 mole of a compound. Otherwise, we will not be able to, never be able to fix it. Because 10 mole will have different value, 10 times higher value than for what is there for the 1 mole. So let's compare for the one. Standard enthalpy change for the formation of 1 mole of a compound from, now this is very important. We can form a compound in many different ways from its element. So we need to make, so compound can be prepared in many different ways. Okay. For consideration of standard enthalpy of formation, you need to prepare the compound from its element. In there, most stable elements also have different states. Standard states of aggregation. This is also known as reference state. So this is called standard molar enthalpy change. You can write molar because it is for 1 mole. Is it clear or not? You put a subscript F. So let me give you example. Are you getting my point? So I am asking you which of the following equations are not written, I am going to write, are going to represent the standard enthalpy of formation of calcium carbonate. This is a compound. So which equation is basically indicating the standard enthalpy of formation of calcium carbonate? Option A, Carbon has different allotropes. You have studied in your class 10. Or we can take carbon as gases also. So everywhere we are making CaCO3. We are writing a balanced equation which is actually resulting into the formation of CaCO3. Are you getting my point or not?
Yeah.
Yes, sir.
The equations are balanced. So if I want to write the equation which can correctly represent the enthalpy of formation of calcium carbonate, what that equation should be? Can
A.
any equation, yeah, just I'm writing one more option, okay? So can any equation be used to represent the enthalpy of formation, molar enthalpy of formation, standard molar enthalpy of formation of CaCO3? Or do
No, it has
I
a
need
specific
to
one.
be, yeah, hmm, it need to be very specific, yeah. Hmm. So which equation can ideally represent the enthalpy of formation of calcium carbonate?
A.
A is the most common, right? Aisha, Nabila. But you need to
Mm,
get back to the definition. Read the definition very carefully. So which equation can be used to represent the enthalpy of formation of 1 mole of compound? Molar means 1 mole. Okay. Do remember that. Now. So molar
is it
enthalpy
B?
of that should be from
So is it B?
yeah, you are very close to the answer. That should be from elements, pure elements. Okay, that you should take care of.
Mm,
Other thing is what I've written in there. Elements, carbon can be in diamond form, carbon you can be written, equation can be written in graphite, okay, or it could be
mm,
gaseous. You need to take that element, the most stable standard state of element at 298 K and 1 bar. So these are not the elements, first of all, these are compounds. Got it? Aisha, Nabila,
yes,
Maha.
yes.
So
Yes.
I'm going to reject. I'm going to reject this. Option B, calcium is element, oxygen is element. That is true. Good. But carbon is the element, but what is written in the bracket?
Gas.
Gas. Is the carbon normally, is it in the room temperature 298 K 1 bar? Is it in the gaseous form? Or is it the solid?
Yes.
It's not
Solid.
in gases, it's solid. So just because of this, it has gone wrong. Definitely this is wrong because this is not representing the enthalpy of formation of calcium carbonate, because I have taken two of the substances as compounds. This is correct. Calcium is there in the elemental form, solid. The most stable standard state of carbon is graphite. Just remember it. For sulfur, it is rhombic sulfur. You can write it. For sulfur, it is rhombic sulfur. Standard states. Carbon taken in solid form as graphite. Graphite is more stable, little bit more stable than diamond. That is standard state of sulfur is rhombic sulfur. Got it?
Yeah.
Standard
Yes, sir.
state of phosphorus is white phosphorus. I'm not talking about the standard state of oxygen. S represent white. This solid and this is white. Whereas you have different types of allotropes of phosphorus. White phosphorus, red phosphorus, black phosphorus. So white is taken. The standard state of oxygen is O2 gas. Okay. Is it clear?
Yes, sir.
So whenever an element is forming, whenever a compound is forming from its element, taken in their standard states, then whatever the 1 mole of compound which is being formed, then whatever the enthalpy change we are getting under the standard condition, that is actually representing the standard enthalpy of formation from whom? From pure elements in their standard states. That is called enthalpy of formation of a compound. Got it?
Yes, sir.
Okay. Note one more thing. Standard, this is for the compounds. What about elements? So pure elements, actually compounds are formed from elements. And what about the elements? Standard enthalpy of formation of pure elements, for example Br2, in their standard state, Br2 is in liquid, got it, is
Yeah.
taken as
Okay,
0.
sir.
Standard enthalpy of formation of oxygen, liquid oxygen, solid oxygen, or gaseous oxygen?
Okay.
Gaseous.
Gaseous, because the standard state of oxygen is gaseous. Okay. So if somebody asks, normally this has meaning for compounds, standard enthalpy of formation of compounds. So when 1 mole of a compound is formed from elements, pure elements in their standard state. But if somebody asks you, what is the standard enthalpy of formation of pure elements? If somebody asks you like that, so what you should say, the standard enthalpy of formation of pure elements in their standard states, but it is 0. Is it clear?
Yes, sir.
Yeah.
Is it going to be 0? Tell me quickly.
Yes, sir.
Yes or no? I told you for carbon, what state of carbon should be taken
Graphite.
as its graphite. Yeah, exactly. So do keep this in mind. This is not 0. There is a slight
No.
difference. This is not 0. So this is not the standard enthalpy of formation. This is not considered while considering the heat of formation of a compound. You should not take diamond. Okay, you should take graphite. It is actually correct, but it is not the standard state of. I should write it as like this. Not the standard state of carbon. Got it? Is it
Yes, sir.
clear? This is not the
Yes,
standard
sir.
state. Standard state is graphite. Do remember it. This is the thing. 0 kilojoule per mole, and this is kilojoule per mole. Okay. This is not the standard state. So how we are going to use this enthalpy of formation? What is, okay? We have the enthalpy of formation of compounds. Okay, but what we are going to do with it? Okay, they represent equation enthalpy of formation. If it is negative, they in a way it can tell us whether a compound is stable or not. If it is highly negative, then the compound is going to be very stable. If it is positive, then the compound will be less stable. Okay, but there is a very important use. Okay, very simple use. Any reaction, if it is given, So if you have enthalpy of formation, list of enthalpy of formation, they will be given to you in the question itself. Okay, you can calculate the heat of reaction, overall heat of reaction. Let's say, for example, you have A moles of X, okay, and B moles of Y, giving you C moles of Z. The overall heat of reaction is going to be the C times sum of the enthalpy of formation of the products. Z C times S, because you have C moles, minus sum of the enthalpy of formation of reactants. This is the use. So because the time is up, we are going to continue with this in the next class. Okay. But this is quite easy. Even if you get the question, if you have if these are the compounds. So overall heat of reaction is the enthalpy of formation of products minus enthalpy of formation of reactants. Got it? Here.
Yes, sir.
Okay. So this we are going to continue examples and we are going to look, but this is a very powerful tool. They will give you the enthalpy of formation